Welcome back. Happy Friday. I don't have any announcements for today about the course. Are there any questions about anything? Yeah.
Yeah, maybe something I forgot, but how come when drawing the vector loops, we don't have to add those tip to tail to vectors?
Yeah, the question was about drawing vector loops, and this one I drew it with tail to head, then head to tail. So I wasn't doing vectors all head to tail, head to tail. You can choose, and it would just change the signs here. So I have a minus sign here because I drew R3 in the counterclockwise direction. So it's up to you. So you can do either way. Today we're going to do a major final step, and we're going to finish this problem, which we struggled our way through last time. And today we're going to finish up taking the derivatives, which a lot of you were in tutorial this morning, and Taha did a problem, a different geometry problem, and set up loops and was working on derivatives. So we're going to do that again today as a review for you about taking derivatives. I'm going to show you some alternate approaches, and we're going to talk about difficulty of solving them. The main thing I'd like to get out of today is interpreting our answer. So we're going to come back to this question, how we draw those vectors and how that affects our answer. And our goal from this problem was to find theta 3 dot, so rotation rate of our output link, and to find sliding speed, which had something to do with R3 dot. So we're going to find those equations today, and we're going to ask ourselves, what's the direction of those once we find our equations? So we're going to come back and look at the implications for our vector directions here today. So we're going to interpret our vector loop result. And in particular, we're going to be talking about velocity, but the same thing is going to apply for acceleration, which we won't really write out full equations for acceleration today. Any other questions about our basic loop formation or what we did before or from tutorial? Yeah.
I don't know about anybody else, but from yesterday I don't have the same thing written down, the same tangent inverse. I have sine on the top and
Oh, yeah? It should be sine on the top, yeah. Thanks. Good eyes. Good. Okay, so we're going to go through and solve the rest of this problem today. We have these expressions, and I put the 4 key equations. And these are a little different numbers, perhaps. I think we were up to 6 and 7, but this is what we're going to use for today. And we're going to think about our 2 options. So we had these 2 options for taking derivatives. And the first was, let's take the derivative of 1 and 2. Take the time derivative of those. And the second option would be taking the derivative of 3 and 4. So just looking at these, to take the derivative of 3 is not going to be so bad. The derivative of 4, we'd need a inverse tangent derivative rule probably to do that, right? I think you could figure out some way of doing it even if you didn't have that, but it'd be pretty tricky. I think if I want to find R3 dot, that's like sliding speed. If I want to find R3 dot, one option is just take the derivative of this directly. This one is not so bad, so I think that's going to be the better approach. The alternate would be to take the derivative of equation 2 or 1 of those, or both, and then we'd have an algebra problem. We'd have to solve for R3 dot. So the problem with that, and we'll do an example of that in a minute, the problem with that is that you get a big jumble of R3 dots, theta 2 dots, and theta 3 dots. And so we're going to have to, after we take derivatives, we'll have to solve 2 equations for R3 dot. Whereas if we just take the derivative of equation 3, we won't have to do that. So let's do that here. Okay, and the hard part of doing these derivatives, of course, is basically we have to apply our chain rule. So what I'm going to be doing today, I'll try and do this every time we take a derivative. I'm going to underline the things that are varying with respect to time. Right? We're taking a time derivative. We're not taking a derivative with respect to angles. We're taking it with respect to time. So let's list out our constants here. Those are not varying. So constants will be easy to handle. So that's R1, R2, theta 1. Right? Everything else is varying over time. So theta 2. What I'm going to do is I'm going to just underline those so we can remind ourselves. R3 is varying, of course. Theta 2. That's everything, right? Let me actually go ahead and do this for our main equations too, our original equations. Theta 2, theta 3, R3, theta 3, R3, theta 2. So those are the things that are varying with respect to time. So we're going to have to do chain rule on those, right? Chain rule. So time derivative of sine with respect to time is going to be cosine times the derivative of what's inside the cosine, which is theta, right? Times theta dot. So that's our chain rule. So we're going to have to do that a whole bunch. So now we're kind of ready to do our time derivative of 3. We're going to have to use product rule a bunch here, power rule maybe. Okay, so let's do this. We're often going to have big equations, so I'm going to struggle to fit them on the board here. Left-hand side just becomes R3 dot. Okay, so we're going to have a 1/2 out front, and then we're going to have everything inside the parentheses to the power negative 1/2. That's power rule times derivative of what's inside. Okay, so everything inside here, R1 squared plus R2 squared minus 2R1 R2 cosine theta 2. Okay, and it's to the negative 1/2 now. And now we take the derivative of everything that's inside that bracket. And now we need to think about what's varying. It's just theta 2. Just theta 2. So that simplifies things here. So we're going to have, and I give you the derivative of sine. Derivative of cosine is going to be negative sine. And theta 2. And now we're going to have this theta 2 dot appear there. Okay, so this is our chain rule. You're going to have to use that a lot. Especially if you're taking derivatives of your solved equations. These 3 and 4, these were our solved equations. So they may be complicated, and you'll have to deploy all your calculus tricks. Okay, but the good news is, once we solve it, we're done. We can say, we know everything here, right? Theta 2 is the input. Theta 2 dot, the input angle. Theta 2 dot's the input speed. We know that. We're good. So you can plug this in directly. You have a, here. Oh, it was negative there, and I did double negative. Yeah, thank you. I don't see any more hands up. I think I'm doing good so far. Excellent. So this is clearly a win. Like that's a really easy one. We just used our chain rule, power rule, and we're done. So that was a good choice, taking time derivative of 3. But next, let's find theta 3 dot. Theta 3 dot. Okay, and I can never remember a whole bunch of derivative rules of trigonometric functions and inverse trig functions. You'll have to put some on your equation sheet. I suggest if you're using them, put them on there. Of course, if you don't have any of those, you can always go back to equation 1 and 2. And those are always going to be easy to do derivatives. Right? Derivative of 1, it's just a r times cosine or r times sine. So those are always going to be easy. But if you have them, let's use them. So time derivative of inverse tangent plus okay, so if you have this, we can use it. U is everything inside there. So I'm just going to write that out here. And we're going to take the derivative of that, right, du dt. So let's do that first. Where are we looking here? Inverse tangent, there it is. I don't like to use quotient rule personally, so I'm going to write it out so we can use sine rule or product rule. Okay, got my sines and cosines right. Okay, so I just rewrote it here so I can do, we'll take that time derivative, and let me use my, I can find my blue. What's varying with respect to time? We'll always have to remind ourselves. It's really easy to drop some terms. Okay, it's just those two angles, right? R1 and R2 are not varying, so those are constants. So this one's not going to be too bad. We're going to have two terms appear here. Let's do derivative of the first times the second. So derivative of sine is cosine times theta 2 dot. Okay, so that was derivative of the first term, and then we're just going to multiply that by the second. Now we're going to do first times derivative of the second. Okay, so we have, we're going to have the same thing to the power -2 times derivative of what's inside, which is going to be R2 minus sine theta 2 dot. And R1's a constant, so that isn't going to appear. Any issues? Yeah.
To make the second term negative, we drop the R1.
This-
Multiply by the exponent, right?
This one here? Oh, we multiplied, so it should be -1 out front here. Thank you. Yeah. Personally, I have to do these very slowly to catch all these terms, and I try not to skip steps when I'm trying to do them accurately. Okay, so this is good. This is du dt. So basically, we can write out the whole thing now. We have u. So our final solution now, it's going to be really big, right? 1 over 1 plus u squared. Oh, geez, right? It gets really big. du dt. I'm not going to write out the whole thing. Okay, I think that captures it, and you put du dt, write it out again on the numerator there. Okay, so this isn't too bad. So if you have a function that you can take a derivative of, nicely, you have some nicely packaged rule for you, you can do it. It's not too bad. Is there a question?
Could we just leave it in terms of u, if u is defined?
Yeah, so on the test, the question is, what do we need to plug in? I didn't plug it in because it's too big for me to put on the board. Maybe I want it to be clear. So you don't have to have it written out in full with every term if it's really big. And if you want to define some things like u, and then, or even du dt, and write it out like this. Don't go wild with like too many things that are defined all over your page. We need to be able to find it. But if you want to do a little bit of that, I understand on the test it takes time to write out. Yeah. I don't want to test your ability to just copy the same thing all over and over. And the next step is going to be accelerations, right? this problem, I'm just worrying about velocities. Acceleration, right? We'd have to do another derivative. They're going to get huge, right? Accelerations are going to get really big equations. So I think this was a nice way of finding. That was a nice way of finding the eta 3 dot. It wasn't too bad. But I would like to do one problem. Oh yeah, this can be. Oftentimes they can be simplified. So you can deploy some trig identities is usually where to look for simplification. So here's just I'll put dot, dot, dot. Simplify, we're finding theta 3 dot. The book actually solves this one. So check out the book if you want to see, for example, they simplify it without explaining how. This one, it doesn't, after simplification, it's not that huge. I'm not going to ask you to simplify things necessarily. If you see simplifications, that would be nice. You can apply them. And it's also a great way of, if you can simplify early, it's going to make your derivatives easier, or solving algebraic problems much easier because you have fewer terms. So it is a great thing to look for. And if you see any simplifications in problems that you're solving, keep those in mind, and that may apply for another problem. Because a lot of mechanisms have very similar solution methods, right? A lot of mechanisms actually are described by a triangle. So the exact solutions we're deriving here can apply to other mechanisms as well. But that's going to appear in other cases too, or maybe portions of your equations are basically going to be the same from mechanism to mechanism. Okay, I'd like to do an example though. We used our solved equations. I call them 3 and 4. That's what we did here. Let's take a look at what the problem would be. Let's say you didn't have this trig derivative, inverse tangent derivative equation. And you said, okay, let's go back to 1 and 2. Let's go back to 1 and 2. So we'll call this the other method. We're going to take the derivative 1 with respect to time, and then we'll take the derivative of 2 with respect to time. So let's just dive into it. Equation 1, everything's on the left-hand side, which is fine. So there's my first term. Second term, double negative, goes to positive. And third term, R1, is a constant, so it doesn't appear here. Okay, so that's pretty quick. And that's as hard as it gets for the derivatives. They're always going to be the same. Equation 1 and 2 are always just going to be r times cosine. And then vertical components, r times sine. This one should be negative. Oh, I made a mistake, right? R3 is varying over time, so I did drop a term. Now I see it. R3 is also varying. Okay, very good. So now we're ready for this one. Minus R3 dot sine okay, so we could call this equation 5 and equation 6. And now we could solve these for our two unknowns, theta 3 dot and R3 dot. So let's just look at what the form of these are. We have R3 dot here. We have theta 3 dot here. So they're both in the first equation. Some ringing. I'm not sure what it is. Something here. There we go. Down here, R3 dot and theta 3 dot. So both equations have both unknowns. So to solve this, you need to solve them simultaneously. My take-home message for you is that you can use hybrid approach So you could solve, let's say you already had found theta 3 dot. You can plug that in, right? We already have it. So you could plug it in here and solve for r3 dot in one. That would be pretty straightforward, right? Solving for theta 3 dot. It only appears once in here. You can just solve for it there. Same thing here. If we plugged in, r3 dot and theta 3 dot only appear one in either equation. So you can use either of these if you found part of it in the first step. If you didn't want to do that or you hadn't solved them, maybe we don't need to go through the whole solution, but let's find theta 3 dot. So I'd like you to think here, what's your algebraic approach going to be? Theta 3 dot is here and here. So let's assume we don't know r3 dot. We haven't solved that. So just like last time, the goal, which is what I flubbed up a little bit, was that we need to eliminate r3 dot, because that's our other unknown. Need to eliminate that. So we can look at these two. Your strategy can be look at these two r3 dots and say, how can we eliminate them? So you can, last time we used that sine squared plus cosine squared equals 1. So that could work here. You could do equation 5 squared minus equation 6 squared, and you'd get that. There's going to be a lot of terms. So this one, let's try a different tack. We have sine theta 3 here and cosine theta 3 here. So what if I just subtract those and make them equivalent? Let me show you what I mean. Let's take equation 5 times sine theta 3. And let's add that to equation 6 times cosine theta 3. Okay, so that would eliminate both of these r3 dot terms. 5 times sine, 6 times cosine. So it's designed to eliminate our other unknown, r3 dot. Let's give it a quick try here. It seems like it's going to get really huge equation, but that term's going to disappear completely. So it's not going to be so bad. R2 sine theta 2. This is equation 5 times sine theta 3. Theta 2 dot. So we're going to get sine squared for the second term. Okay, in the third term, we expect to go away. Cosine theta 3, sine theta 3. Okay, so that's 5 times sine 3. And we're going to add now equation 6 times cosine theta 3. Okay, this is the one that's we should eliminate it. So we have minus r3 dot. Okay, so we have the same terms but opposite signs here. So those two will cancel. And then we just have our last one. And theta 3 dot. Okay, good. We see here sine squareds. Anytime you see a sine squared, you can ask, is there a cosine squared of the same term? And yeah, this works out, but they're one is plus and one is minus, so those are not going to cancel each other. Here we have sine squared and cosine squared pluses, right? So these terms are they could combine those. Sine squared plus cosine squared equals 1. So that's from those two terms on the left. And the rest just carry along here. Okay, good. But now we have it to a form where we can see it's easy to solve for theta 3 dot now. I see a couple hands. Do I have a issue?
I'm just asking, could you repeat how you got R2 theta dot 2?
Which term?
Like the leftmost term that you just wrote, like how did you combine the...
Here. So this is sine. Oh. We can't do that. Thanks. Maybe that's what the other hands were as well. We can't do that. 2 and 2s and 3s. Yeah. So those can't simplify. No. So we need those two terms here. So all that simplifies is that single one. Yeah. Thanks for pointing that. Another question?
Professor, for equation 5, the R2 finds theta 2 go to negative, and the last one is negative.
You think these two should both be negative? So that would change some of these here. Let's see, where's our equation 1? It's gone, right? Derivative of cosine, it should be negative sine. Yeah. And this should be negative r dot, right? That's the term I forgot and added. Yeah. Okay, a few corrections. Thank you. So let's just propagate these into here. So that affects our whole method, right? So now if we want this one and this one to cancel, they're both the same sign. So now we need to do a subtraction. Same method, we're just canceling them. So subtraction. So we'll just put a negative sign, positive, and positive. Okay, a few corrections. Process isn't affected. We just changed some signs. Thanks for pointing that out. Yeah. Good. Okay, so the goal here, we're finding theta 3 dot. So this is a form we can solve for theta 3 dot, right? We can write theta 3 dot out as an equation. Can I do it without making a mistake here? In one step, I don't think so. Theta 3 dot. So let me just group my theta 3 dot terms. Okay, now we have, let's see, this is what I was hunting for before, was a sine squared plus a cosine squared. Sine squared plus a cosine squared. I think those are good now. So this is going to go to 1 now. Times R3. 1 times R3. Okay, there we go. All right, so that was the theta 3 dot terms. Left over is R2 times theta 2 dot. There's 2 of those terms. And they're going to be minus sine theta 2, sine theta 3, minus cosine theta 2, cosine theta 3. And I think that's everything. Okay, so theta 3 dot will just be negative this term divided by R3, right? Just solving for theta 3 dot. My board's out of space, so I'll just leave it that for you. You can add that last step to your notes. Yeah?
Please correct me if I'm wrong, because I don't remember, but doesn't that look like, I don't know, cosine A plus B, sine A plus B, one of those, like the last term over there? Like, can we simplify?
Can this one be simplified?
Yeah. I don't know.
Yeah. I think it's going to be like cosine of theta 2 minus theta 3,
I'll take it.
one of those. Is anyone really good with those? You can look them up. I think you're right that is going to, you could simplify that one. Sine or cosine of one of the angles minus the other. Yeah. optionally, you could simplify that. And that would, I mean, if you're taking a second derivative later, that could make that process easier. Although then you have to take the derivative of that function, which you just have to keep track of everything. Okay, any other questions about our process here? So you get to choose these methods. You see, if I try to solve them on a timeline, you need practice to be able to do them correctly. Sign errors are going to be really easy to make. I make them all the time. With some practice, you can reduce those. The last thing we're going to look at is interpreting our answer. So let's get our mechanism up here. So we have equations for r3 dot and theta 3 dot. Those are our solutions, right? Velocities of the output. So what does it mean for, let's say, for one of those to be positive or negative? Theta 3 is going to be easier. So theta 3 dot, let's say theta 3 dot is positive. Let's say you plug this into MATLAB, you plug in all your numbers for some input of theta 2 dot, and let's say you get, that. MATLAB spits out +1 radian per second. What does that mean for length 3? Is that clockwise or counterclockwise? I hear counterclockwise. So we need to think about how the angle's defined. I pointed the vector up that way. So you can define your angle from that. So the way to think about it is a positive theta 3 dot means theta 3 is getting bigger. It's getting bigger. So length 3 should be going counterclockwise. So our interpretation of that is counterclockwise. Okay, and if you're giving an answer to someone, giving an answer to me, you need to give an interpretation. You need to give an interpretation. Like positive means counterclockwise. Okay, and it all depends on how you define your angles. Theta dots, rotation rates are usually all pretty straightforward. R dots are much more difficult. So what if R dot came out to 1 centimeter per second plus? So positive. How do we interpret that? So R3, it's what? It's the length between O3 and this point up here, B. But which B is it? We have multiple B's, right? It's a slider contact. So this is like velocity polygon language, thinking about these as different points. So which B is it pointing to when we're thinking about the sliding motion? Would it be B on, B2, B4, those are over there. We also, it could be, or it should be like B3 or B4. B4 is like the same as B2 because they're connected by a turning pair. Okay, so is it B on 3 or is it B on 4? B on 3. Let's think about this. So this could be velocity. In velocity polygon language, we'd write velocity of B something. We'll say like velocity of one of these relative to the other. So B3 is on length 3, right? B3 is on length 3. So if we drew out length 3 here, and we drew it just up to point B, there's B3 at the halfway up length 3. And it's on length 3, right? So the length, this length here is not changing. Right? B3 it's a dot on length 3. So B3 is not getting any further away from this point O3. So no, it can't be velocity of B3 relative to the pivot. It has to be the other one, B4. So 4 is moving up and down the slide. So this is really the velocity of that point B4. Right? If length 4 goes up the slide, this vector R3 is going to get longer. So this vector R3, I'm going to write out what it actually means. And I suggest you do this. Anytime you have a slider especially, it's hard to interpret them. So it's the distance, or points, to point B4 from the ground O3. Okay, and R3 as a lowercase, it's just the distance. It's the distance between the base pivot and B4. So that's what we need. That's what we need to interpret these. So our interpretation of a positive value, let's think about it with this context. R3 is getting longer. This end is pinned to the ground. We draw here, it's pinned to the ground. And it's getting longer. So that means that link 4 should be moving up the slide. Or you could say B4 is moving up the slide, right? Because that's at the end here. It's pointing to B4. So we'll say B4 positive R3 dot means B4 is moving up that way. Okay, and that's like this velocity of B4 relative to B3 is that direction. So that's how we can kind of convert between our different ways of describing relative velocities. We have this nice precise language from velocity polygons. It's very explicit, B4 relative to B3, and we can draw the direction. And you could draw it on here. Would be another way of expressing that. And a positive value means up this way. Negative value means back the other direction. Questions about that? Yeah.
Could you please explain why, like, what's the difference between B3 and B4 and why B3 is not what it is?
Yeah, the question is about the difference between B3 and B4. So we have the slider, link 4, and it has point B4 on it. And it's going up and down this slide, right? So this vector here, R3, like we chose what to attach it to. So you could draw a vector from the base to this point B3, but that doesn't capture the motion, right? R3 needs to connect with R2. And R2, the tip of R2 is coming here and traveling with link 4. So really, R3 points from the base pivot up to B4. It points to B4. So it needs to travel, as link 2 goes around, link 3 needs to get longer so that our triangle is preserved.
B3 won't change?
B3 doesn't change. No, B3 is on link 3. It's stationary right there. That's our velocity polygon kind of way of thinking about it. Which for velocity polygons, it's not a general solution. But what we're doing here is a general solution, meaning even when you move it, let's say we moved link 2 up to 10 degrees counterclockwise, our polygon, our triangle here would change a little bit. So these vectors will track with all of our links. So this is always going to be true, even you crank it all the way around, and our triangle is going to change shape. So they're going to track with our links. Yeah, this is velocity polygon thinking, which is the snapshot method. So it's a fine way of describing velocities. This is maybe the most general way. Positive R3 dot means link 4 is going up the slide. That would be a way of writing it out. So positive R3 dot means link 4 moving away from O3, moving up the slide. So the tricky part now, I chose to draw R3 up that way. And we interpreted what a positive R3 dot would mean. What happens if we had chosen it the other way? How would we do our interpretation? So I'm going to draw like just a second version of my loop. And this one has R3 pointing down. And R1, we can keep that the same. Okay, so R3 is flipped. So all of our equations would need to change, right? It's a different loop. So our loop equation would be R2 plus R3 minus R1. Okay, so it's flipped, and we'd have to redo our whole solution. It turns out it's just like a bunch of minus signs on all of the R3 terms. We also have a different angle for 3. So we'll call this prime here. That's our new one, prime. So we have O3 prime. It's defined differently. It's 180 degrees plus O3. Okay, but let's assume you went through the solution and you solved for R3 dot, the prime version. We had this written out. And let's say you calculated a positive value. So positive 1 centimeter per second. How do we interpret that? Previously, we said a positive value meant link force moving up the slide. What about this time? R3 is pointing down. So this one's a little trickier. Does it mean it's moving, the link force moving down the slide or up the slide for a positive value? So the way to think about it, just think about the vector in question. So I'm going to draw it out separate here, R3. And you need to think, is one end of it fixed somehow? And that's going to be a common scenario, or it'll have some constraint on it. And yes, the tip is fixed, right? The tip is at this O3 point. So I'll draw it here, be really clear that it's fixed. So a positive R3 dot, that means R3 is getting longer. R3 getting longer. So does that mean, right, and on the back end here, as we said before, that's point B4. If it's getting longer and the tip is fixed here, that means B4 must be going up still. Right? It's getting longer, but the tip is fixed. So the tail must be going that way. So the answer, or the interpretation, is the same in this case. So our interpretation is still a positive R3 dot means link 4 is moving up away from our base, O3. Same interpretation. This one's a little weirder though, because it's on the tail instead of the head, but it comes out the same. So you need to think about how your vector is fixed, or you'll mess that one up. Yeah.
Seem a bit surprised that it's the same interpretation. Are there instances where the interpretation reverses if you reverse the vectors?
Are there cases where, so this one was the same interpretation. Are there cases where it would be different when you reverse the vector? Different interpretation? No, because r dot is not about the direction that it's pointing. R dot is about the change in length. So actually it doesn't matter. We could ignore the head and just say, how's that distance changing? And that's all you need to know. So actually for interpreting your r dots, you don't even need to think about the head. It's just a vector connecting those, and it's getting longer, so that end goes up. If you want to avoid this, if this is causing you errors, you can choose which to do. You could choose R3 or R3 prime. And if you point your vectors up, the interpretation is easier. Or if you point them away from the fixed point, I should say. If you point them away from fixed points, it makes this interpretation was easier up here. This one is kind of like the negative interpretation. It works out the same. There's no problem with it. But pointing them away from fixed base points, it avoids that little trap. Any questions about that? So our remaining topics for vector loops, and Taha already did a little bit of this. I'm going to talk a little bit more about two-loop mechanisms. This one we did here was a single loop. Taha did an example that required two loops. So I'm going to touch on that again because that's it's a difficult question. When do you need two loops to describe your mechanism? And then you get twice as many equations, and you go through and solve them. And the other thing that we need to address is sometimes we're going to get multiple solutions. Multiple solutions. And that's going to occur, we're going to have basically a solution with a plus or minus. And there's going to be two solutions. And this comes back to a mechanism that we've seen where it's going to occur every time for a mechanism that we've seen, which is a 4-bar. I'll draw a really tiny one here. If this is my 4-bar mechanism, and this is link 2 is here, and I give you 2 more links, link 3 and link 4. There's 2 ways you can put them on here, right? One solution is going to be here, and the other solution is going to be there. And the cool thing is our equations will tell you that there's 2 solutions. You'll see it. Like we'll have a quadratic equation for this one. We'll have a quadratic equation. Solution has a plus and a minus. It'll tell you both. And it'll tell you that there's 2, and you can solve for both, which is really cool output of this whole process. It doesn't lead to a surprise that there's 2. We'll see it right in the math. And you could plot out both. And we've kind of talked about the implications of this before, right? We were kind of cranking 4 bars around, and we saw that it would switch between those 2 solutions at the change point. But if you're plotting in a MATLAB, you can tell your code only choose solution 1 or only choose solution 2, something like that, or whatever you want. So that's what we'll do. We'll see these 2 things, the last topics for loop method. Thanks, everyone. Have a great weekend.